Hello YouTubers, welcome to yet another edition in my series where I create a Commodore 64 on an FPGA. In the previous video we managed to get a static frame displayed on the screen, and in this video we're gonna attempt to show the output frame from our Commodore 64 on the FPGA screen. Hope you enjoy it. So here we are with our current Commodore 64 design from the previous time. Our whole Commodore 64 implementation is within this block test 0 block. So here's all the Commodore functionality, and we just take the output frames produced by this block and we write it to SDRAM via this myIPBurst test block. So as you might possibly remember from the last time, our Commodore is only currently able to write VIC-II frames to SD memory and is currently not able to read them back and display it on the VGA screen. So as mentioned in this video, we will attempt to provide VGA output to our design. So we start off by introducing a VGA to this block design. So we search for VGA and we add it. So just flip back to this design and we move it just down to about here. And let's just zoom in again. Okay. So this block is more or less the same block we've developed in the previous video where we just want to display a static frame from SDRAM. So let's just want to mention though, there is a couple of changes I had to do to this VGA block. So let's just first go through these changes. Okay. Let us have a look at the differences in the VGA module. For both the VGA module at the end of the previous video and the VGA module that we've modified in this post. So for this comparison, I'm using Melt. Let's see, this is available for most Linux distributions. So here I've already opened up Melt. And we're doing a new file comparison, and on the left side here I have the old version of the file called VGA64 old. So yeah, this is the version of the file in the previous video, and VGA sync frame.v. Now this is the version modified in this video. So now we're gonna compare these two files. Okay. We start off, we see here on the left side our old file have all these registers, VIC, delay 1, 2, 3, 4, 5 being removed, and it's now only contained in a single line for all these sync declarations. But you also see it's been prefixed by this async rec equals true annotation. Now you might remember from the previous post, we also used this to assist in our problem where our image displayed was not static. So here we assigning this as well, for the simple reason I've experienced with the vertical sync when passing it to one of the domains. Sometimes you'll see a frame there's a bit of jitter. So in the end I've seen it's best that we also annotate these synchronizers also with the async equals rec equals true. Okay, so that is the one change. Let us slowly scroll down for the other ones. And here we see another change. Let's just look at this closely. So here you actually see we actually swapped around the bits. Here you concatenate 13 to 16 and then 15 0, but here we start with 15 0 and then 31 16. This is just the way I found in my Commodore 64 implementation. For one other reason, the pixel bits has been reversed, so I had to write it this way. Okay, let's scroll further on. I'm just going to scroll back here. Okay, so the other one you see here is with our A5 implementation. Here is also some interesting things happening. Okay. This part is actually for the Commodore 64 display. This is our previous. So these things got a bit mixed up. But in the Commodore 64, we only are reading when our next vertical position is bigger than 100, but less than 384. Now the reason for that is we only want our frame to display in a small portion of the screen. So we say, okay, we're only going to read from this FIFO if our current vertical position is between 100 and 384. So I see the difference here between the two is 284. So this is more or less the screen we have been working up to this point for our Commodore 64 display. And as well as the horizontal position, we only display fetch data from this FIFO if the horizontal position is between 100 and 505. Okay, here again you see the difference is 505 minus 100 is 405. So then it will read from this FIFO. And if you continue scrolling down, here's the same kind of thing that's happening here, that we only do this within this range. So in this side you say we only output the pixel if it's within this visible region, otherwise we just return a black color. So yeah, that is basically what we'll be seeing on the screen. The Commodore 64 screen in the middle, surrounded by this huge black border. So let's scroll down. Yeah, this is about it. Okay, now that we've covered the changes in our VGA block, let's continue to link up our VGA block to our design so we can display VIC-II frames. So secondly, okay, we've added this VGA block, and secondly, we need to add a block that will enable us to get information back from SDRAM. So in order to do that, we add another block. So we search for burst. Okay, and we got two blocks. The burst test is the one in our existing design, which we use to write information to SDRAM. And the one we're going to add now is this my IP burst read test. And this is the same block we've used in the previous block. So let's just add that. Okay, here we've added. I'm just going to move it down a bit. Okay, here we are. And now, yeah, we have two burst blocks, one for doing writes and another one for doing reads. Now, currently, we've only got one master XI port connected, so we'll need to have another one to do both the reads and the writes. So probably a good place to start is just to remove these existing XI helper blocks, like this XI Smart Connect and the PS70 XI peripherals. So let's just start by doing that. So I'm going to delete this one. I'm also going to delete this one. Okay, so all these helper blocks is now being removed. Next thing we should do is add an additional slave port to our processing system. Currently there's only this one, so let's just add another one. So double click on this block, and we go to PSPL configuration and GP slave interface. And as I mentioned previously, only the one interface is selected, so let's just select the other one and we hit OK. Now your processing system blocks should have additional ports. So you see there's now 2 instead of 1. Yeah, what should we do next? Next, we should just wire up everything again. So we're going to make use of this designer assistance available. So click this link. And now we just click, okay, firstly we're just going to add these 2 ones. So just hit OK. Okay. You see complaints about conflicting addresses. In a short moment I'll just show you how to resolve that and why it's complaining about this. So just continue. Okay, let's click this link again. Okay, I'm just going to select these remaining XI ports to link up. So just hit OK again. Okay, now more or less got all our master ports connected. So this, we can see, for instance, this my IP bus test XI master port is connected to the slave of a smart interconnect, and this master port of the my IP burst retest is also connected to the smart connect. And you might realize that the output of this smart connect, previously there was only 1 master port, but now there's 2. And we see, okay, the first one is connected to the slave port XIGP0, and the other one is connected to slave port XIGP1. So that's connected. So yeah, as you can see, everything is now being connected. The next thing I just want to show you, if we can come back to that address conflicts we've earlier seen. So let's try to resolve this, and you do this by going to the address editor. I'm just going to make this thing a bit bigger. Okay. Yeah, you see, there's 2 of our blocks, the my IP burst test and the my IP burst retest. Now, every one have a master port attached to it, and in this address editor you can actually map to which addresses it looks to. So we see GP0 DDR low OCM. Okay, just go here. Yeah, so this is the lower 512 meg range. So this is basically all we want to map in our design. All the other mappings like GP0Q, SPI linear, we don't need, and there's a whole bunch of these. And the other thing that you might notice is we have mappings ending with a GP0 and a GP1. Now this is actually overkill. We just want, for the one master port interface, we just want GP0 connected and not GP1, you'll see the same kind of things happening in our the read block. So we have a GP0 and the GP1. So let's just clean up this interface a bit. So for the first one, I just want this GP0 DDR low OCM connected. So for other ones, I'm going to select them and I'm just going to unmap them. So now we only have Xi GP0 mapped via the DDR low OCM. And for the other one, let's just go there. In effect, I only want this GP1 interface. So I'm going to unmap this one. And also these other ones. Okay, just right click and select unmap segment. Great. Okay, now we have one entry for each block. And you see the first one is only for GP0 and GP1. Now, if we do synthesize our design and generating a bit stream, we will not see these address conflicts again. So this takes care of our address mapping for our Xi interface. So let's go back to our block design. Okay, so everything is linked up. So we just need to link up the other parts of our VGA connection. So that is very similar as I've done in my previous video. So I'm just going to link it up and I'm just going to get back in the video when I'm finished. So here I finished up connecting all the links to my VGA test block. So this is more or less the same as in the previous video. I, for instance, added here the extra clock wizard block. Currently I have an existing one. If you just look at the output clock speed again, this was 8 megahertz. So that was the clock for the actual Commodore 64 block, which needs a maximum frequency of 8 megahertz, which is used by the VIC-II, and it's been stepped down to the 2 and the 1 megahertz for other components. And let's just have a look at the other clock component. Now this one is 84.4 megahertz, and this is used by the VGA pixel clock. So this frequency is required to provide the pixels at that specific frequency required by the VGA monitor that I used to show pixels on the screen. That is 1360 pixels wide. Now obviously the input frequency is 100 megahertz. So let's just go back to our design. So this is the clock, extra clock component I've added. And then, as you can see, also exactly as I've done in my previous post, I added some output ports which will go out of the VGA chip on the Zyber board and then connect to the actual VGA port. So VGA red, which is 4 to 0, so 5 bits for the red channel, 5 to 0 for green. So for green we have 6 bits, and for blue also another 4 to 0 bits, which is 5 bits for the blue channel. So we have a RGB 565, and also for the horizontal synchronization as well as the vertical synchronization. So this is about it, and yeah, so you have an input clock, a pixel input clock to the VGA block, and a clock Xi, which we use to get information from the SDRAM, our actual frames to display on the VGA screen, and we just hook them all up. So this is about the whole design. Yeah, let's see if there's other stuff that needs to be connected. Okay. Clock complaints about the GP1 port that needs connected, so let's just say okay. Okay, I think I saw some address conflicts again. Okay, let's just look at the address block again. Okay, doesn't seem the best thing that I've done just now. It seems that it put all together back all the other address mapping. So let's fix that once more. I'm just gonna unwrap this again. Okay, so our burst block is again just mapped to the DDR low OCM. And let's just do the same here. Just unmap this. Okay, so this looks correct. The GP0 for the one and GP1 for the other one. Okay, let's quickly save. And let's go back to our design. Okay. Everything should be synthesizable. So let's start by synthesizing the design. Okay, I'm just gonna fast forward this section again. Okay, and now our synthesis is completed. So let's see if we can kick off our bitstream generation. Okay, this just started, so this section I'm gonna fast forward again. Okay, our design is finished. So let us look how it looks like on the VGA screen. So let us have a look at the VGA output of our current design. So I'm pointing the camera currently to a VGA screen, and I've got the FPGA board connected to the screen. And on the laptop, I've currently got the Xilinx SDK open. So let's start off by programming the board. Just gonna do that quickly. Okay, it's programmed, so now let us just fire off a program again on the ARM processor. So we do that, and we wait. Okay, as you can see, it started up some random stuff on the screen you will not actually see on a normal Commodore 64, but this is just a side effect of code I need to add in the startup. So for the dual port block RAM, the main Commodore 64 kilobyte RAM. So that's the reason for that random garbage in the beginning. Yeah, as you can see, here's the final welcome screen. Of course, we're still missing the flashing cursor. Yeah, this is about how the design look at the moment. And yeah, it obviously doesn't fill the whole screen at the moment. So as time goes by, we can maybe look to see if we can add a Verilog module that can actually increase the size. It fills the whole screen. This concludes this video. In the next video, we'll attempt to implement a flashing cursor on the Commodore 64 Welcome screen. Till next time.